Welcome to CS1104 Computer Systems. This is the Unit 2 lecture part 2. During this lecture, we're going to look at some Boolean circuits to do arithmetic. Now, in the previous lecture, we talked a little bit about the idea of adding and subtracting binary numbers. And I know you're not going to probably believe me now on this, and you will agree with me by the end of this course. Adding and subtracting numbers is pretty much everything that we need to have in order to have a functioning computer system. In fact, the primary thing that we're going to do in our CPU as we develop it and as we create a computer system around that is adding and subtracting numbers. So how exactly do we do that? Well, the way that we're going to do that is we're going to use something called an adder. So an adder is essentially just a circuit that allows us to kind of add numbers together. And we're going to build that adder circuit out of gates. Now, we talked a little bit about gates in the first unit. We looked at how we create logic gates using transistors and the properties of transistors. And essentially what we're going to do is we're going to start implementing some of these circuits using those gates. And the first thing we want to look at is an adder circuit. So an adder circuit essentially has, particularly when we're looking at adding binary numbers, has the following truth table or characteristics. So 0 and 0 means I have an output, or sum if you want to call it that, of 0, and I might have a carry value. 0 and 1, it means I have a sum of 1 with a carry value of 0. 1 and 0 means I have, and meaning that I'm adding 1 to 0. It means I have an output of 1 and a carry value of 0, and 1 plus 1 is 0 with a carry value going to the next position over of 1. So how do we actually build that? Well, let's look at this. Essentially, I can build that circuit by using two gates. So the first gate is I'm going to have something called an exclusive OR. And the second gate is an AND gate. So we know that in an AND gate, when A and B have a value of 1, it will have a value of 1 as an output value. But in no other condition will it. And we also know that the exclusive OR says that I'm going to have an output of 1 if A is 1 or B is 1, but not if both of them are 1, and not if neither one is 1. So when I put this functionality together and I create a truth table on this, what we're going to find is that I've actually implemented the truth table that's represented here in the adder circuit. Now, one of the problems that I have with that circuit is the fact that it's not very useful, and we refer to this actually as a half adder. And the reason we do that is because one of the things I don't have in this is the ability to accommodate for a carry-in operation. So I've got a carry-out operation, but I don't have a carry-in. So it really isn't going to do me a lot of good to just add together one bit. What I really need to be able to do is put these together such that I can add together quite a number of bits, maybe 4 bits or 8 bits, 16, 32, 64, whatever the architecture is of the computer system that I'm dealing with. So again, difference in a full adder circuit, and this gives you a sense of the full adder circuit and its truth table, is that the full adder allows me to bring that carry-in bit from a preceding operation. So I can just basically build this particular circuit and then put it together with several more of them. So if I string a whole series of these circuits in together, where the carry out of one becomes the carry in of the next one, I can actually develop a circuit that will allow me to add together a binary number of pretty much any size. And that's exactly what you see here. In fact, this is a 4-bit adder circuit that's been developed and implemented with the Logism tool. Logism is one of the tools that we will be using in this class. In fact, I'm going to ask all of you to go out and actually build a 4-bit adder circuit. And what happens here is that I can take the first number in, and again, keep in mind these numbers are in binary, and I'm going to put it on the A input. So you see I have 1, 2, 3, 4 A inputs. So that means a 4-bit number that is going to be added to a second 4-bit number, which is all the B's right here. So when I put all the, for example, if I were to put 1, 0, 1, 1 as my 1 number, and then add it to 0, 0, 0, 1, then I would expect to see an output over here, which is the addition of those two 4-bit binary numbers. And essentially that's how the adder circuit works. And multiplexers is the next thing that we want to talk about. Adder is a very important circuit. We are going to use an adder to do both the addition and subtraction. We know now that in subtraction, all I'm going to do is I'm going to take and convert my second number into 2's complement and then add it to the first number. Multiplexers are another very important general circuit that kind of falls in this category that we refer to as combination or combinatorial circuits or combinatorial logic. And in this particular circuit, and you'll find that this is extremely valuable, what happens in a multiplexer is that I may have multiple inputs coming in and I have one going out, and when I have multiple inputs coming in and only one coming out, where I select from the available inputs to send the signal out, we refer to that as a demultiplexer. And a multiplexer is where I have one signal coming in and multiple ones coming out. And again, the way that I select which one is going to be actually selected as the appropriate input or as the appropriate output, depending on whether we're doing this with a multiplexer or a demultiplexer, is with a series of what we refer to as select bits. So if I were to look at an example of a multiplexer, you'll notice here that all of these D0, 1, 2, 3, 4, 5, 6, and through 7, these are all potential inputs where I have these bits off to the side. S0, 1, and 2 determines which one is actually going to be selected. So if you think about it, in binary, 0, 0, 0 produces 0. That's one combination. And so if the values of S0, S1, and S2 are 0, 0, and 0, then it's going to select D0 as the input to send to the output, which is F. On the other hand, if I were to have the values of 0, 1, and 1, it's going to select D3. So whatever's coming in on D3, and this is selected as 0, 1, and 1, then that output's going to be sent through to F. And that's essentially how a multiplexer works. And as we get into designing our ALU, you're going to find that this is extremely valuable. I can have a variety of different size multiplexers, and what winds up happening is the more inputs and or outputs, depending upon if it's a multiplexer, the larger the number of select bits. So if I think about it, if I have 2 inputs, that means I'm choosing between 0 and 1. I really only need 1 select bit, right? Because if I'm making no selection, it's 0, and if I am making the selection, it's 1. So for a 2-channel multiplexer, I only need to have 1 select bit. However, if I have 2 select bits, I can effectively control up to 4, 3 select bits up to 8, and 4 select bits I can control up to 16 inputs and or outputs. The final thing we want to talk about is why is all this important? And when you look at what the central portion of the central processing unit in a computer, it's called the ALU, and that stands for the Arithmetic Logic Unit. And what the Arithmetic Logic Unit does is it does all of the actual computations. So there are very, very simple computations that any CPU does. And this is a great example of what the kinds of things a typical CPU might be able to do. And I told you the most important ones are really to do addition and subtraction, and we can see that we have right here. We have an add function and a subtract function. And all that this add function is I'm going to put in a series of the full adder circuits that will add 2 binary numbers. Now in this particular case, it's suggesting that there's 16 bits, so there would be 16 of those full adder circuits in sequence. The subtractor circuit is very similar. It's going to have 16 of the full adder circuits, and they're going to be preceded by some gates that will actually convert one of those numbers into 2's complement. I might have a shift, and a shift basically just shifts the bits over by 1. I might perform a bitwise AND. So think of a whole bunch of AND gates that I'm applying against each of the 16 inputs, the 16 bits in the first number, and each of the 16 bits in the second number. I have an OR. I might have a pass-through. In other words, what a pass does is it simply says, turn this guy on, and whatever came in, I'm going to send to the output. And I may have some arbitrary function. So, many CPUs may have, more sophisticated capabilities than this. But, quite frankly, none of them get all that much more complicated than what you're seeing right here. Now, this is where that multiplexer comes into play. So think of each of these as being inputs into this multiplexer, and the way that I determine what function this CPU is going to do, what computation is it going to do right now, is that I select one of them to turn on to send the output to. So they're all going to do the computation. It's just one of them is going to get elected to send the output to, and that's literally how I determine what computation is going to be done within the CPU. By the way, this is kind of the symbol that you will typically see of an ALU, and how it's used is you oftentimes are going to have a couple of registers. So essentially what's going to happen in our ALU, I'm going to have two registers. I'm going to load those registers, and by the way, we'll talk a little bit about what a register is in the next unit, but what a register is, it's basically a memory structure that's going to hold one word of whatever number of bits I'm dealing with. So essentially I have an A register and a B register, and essentially this forms that A input, B input that we saw on the previous screen. These select bits off to the side are essentially just telling us what operation we're going to perform. So using this combination of select bits, I'm going to turn on one of these features. Maybe it's going to be the add circuit, maybe it's going to be the subtract circuit, and maybe it's going to be the shift, the and, or the or. But essentially I'm going to turn one of them on, and essentially using that multiplexer, which is assumed to be inside of the ALU, I'm going to send one of those as the output. And that, by the way, is the foundation of exactly what the ALU is doing. Now, you're going to see there's some additional outputs out here, and a lot of times we refer to these as control bits. And they're going to tell us some really important things, such as whether the output that was computed was 0, positive or negative, and it might also have some information about whether or not an overflow occurred, or whether or not there was a carry value that came out. So these are important. We're going to cover them a little bit later when we get into the different logic. But you can see in this particular example, we're showing that what the different functions are. Now, what's really interesting is these functions. Add the two numbers together, subtract them, add one, which by the way is an increment, or sometimes refer to it as a shift. Or subtract one here, add one, perform a bitwise and. This is a perform a bitwise or, not just basically inverts the output. So if it's coming out as a 0, it's going to make it into a 1. And this actually is an exclusive AND here. But these form the core functions that the actual CPU is going to do. And as we get into looking at the assembler, we're going to realize that's essentially the core of what our computers are doing. It just does so many of these types of operations, we can put them together to create the familiar structures that we would be more comfortable and familiar with in other programming languages.